Okay, everyone. We're going to finish up chapter 6 today, so I'm going to send you out a video for chapter 6. Basically, we left off, so this will be part 3 of the chapter 6. We left off here where we were, what percentage of people have IQ scores. This is definitely a test type question, so make sure you go over this one in the videos. So we're going to go over here to the end of chapter 6. And it says, for 14-year-old boys, the distribution of cholesterol is approximately normal with a mean of 170 milligrams with standard deviation of 30 milligrams per DL deciliter or something like that. I'm not exactly sure. What is the first quartile of the distribution? So the first thing we notice is they start talking about quartiles again. We haven't done quartiles in a while. I don't remember talking about them recently. That was all the way back in the box plots. But if you guys remember when we talked about box plots, quartiles were basically the way to divide 100% up into 25%. So if they say the first quartile, we're doing the first 25% of the normal curve. And again, another key fact is they told us that it's approximately normal, right? So we're pretty happy that they told us approximately normal, because that means that we now can use our normal CDF function, or we can use the charts in the book or whatever. So it says, what is the first quartile? So I'm going to draw the first quartile. I feel like it's going to be right about here. And then I'm going to shade my 25%. Remember, drawing the picture will help you guys not lose track of what you're doing. Some of you will be like, well, I don't need to do it. I can get it without doing that. And that's fine. But it's going to start feeling like you're just hitting enter on the calculator and you don't actually know what you're finding. So by drawing the picture, it's an attempt to help you not lose track of what's going on. Okay, so please draw the picture for yourself. We know that there is 0.25 in that location, that area. And again, 0.25 area is the same as 0.25 probability. So it says, draw a picture, shade the correct proportion. Okay, done. Part 2, identify the z-score in the table that corresponds to this proportion. So when they say in the table, remember, we're not using the tables. We're going to use our calculator instead. So it says, identify the z-score that corresponds to this proportion. Well, let's first find inverse norm. Okay. And now we know we know that we're dealing with 0.25. Now, the question is it in the right direction? Remember, I always told you that when you're doing inverse norm, the calculator always does it from the left. It goes left to right. So this is actually in the right spot. If it was on the other side, remember, we'd have to do that part where we outsmart the calculator and do it. But since it's on the left already and it's going from left to right, perfect for us, we can just use inverse norm. We know with a mean of 170 and standard deviation of 30. Let's see what we get. So I'm going to go second vars, second distribution, inverse norm, 0.25, 170, 30. Standard deviation of 30. And I get 149 point, 139, or 149 point, let's go with 765 for now. I'll just use 3 decimals for now, okay? The problem is this 149.765, that is not a z-score. That is the answer to the question when it says, what do you want to say? That's the actual value of the cholesterol levels, okay? So that's the 14-year-old boy's actual cholesterol or estimation of it. And that would be the first quartile of the distribution. So we're saying that 149.75 would have 25% of the distribution below it. 25% of the values are below it, okay? Now the problem is they didn't ask for that in part 2. So this is part 1. Part 2 asks for the z-score. So all I do is I say, well, my z-score is worth 149.765 minus my mean, which is 170, all divided by my standard deviation, which is 30. So let's see what we get on the calculator. Let's do 149.765 minus 170 divided by 30. I get negative 0.6745. Okay, so this is my z-score. You know what, let's round it off a little bit. Let's use three decimals. Let's do negative 0.675. Okay, so that is my z-score. So that is the actual answer to problem 2. Okay, now problem 3 says unstandardize with the formula. But the thing is since we used our calculator, they want us to use this formula here and this formula here. So this formula of x equals z times the standard deviation plus the mean plus mu, that wants us to unstandardize it, but we already found the answer. That is this guy over here, 149.765. But just to make sure that we're doing this right, I'm going to go ahead and do it. I'm going to say, well, x is equal to z, which is negative 0.675, times the standard deviation, which is 30, plus the mean, which is 170. Now, I think you already know what's going to happen is we do negative 0.675 times 30 plus 170, and we get 149.75, which is basically the same answer as up here. Now, again, it's a little bit off because we rounded off. So in reality, I would actually take this answer better up here. This one, let's do this one in some fancy. This one right here is probably the better answer. But I just wanted to show you that we're getting the same thing. So by using the calculator in step 1, we actually found the correct answer in step 3. So the calculator can go through and do it for us right away. Okay. So this is how you can unstandardize and standardize, but in reality, the calculator will give you the unstandardized answer already. And if you want to put it back into a z-score, you can just use your normal z formula. Don't let these two formulas freak you out. You already know the z-score formula. And this is just solving for x in the z-score formula. So it's no big deal, okay? And if you want to make sure you know how to do it, you can look over here on the notes. Tells you z means standard deviation. That's what I just did, okay? Okay, let's look at this next one. It says scores on the SAT test. The scores on the SAT test in recent years follow an approximately normal distribution with a mean of 504 and a standard deviation of 111. Okay, well, this sounds pretty straightforward. Okay, so let me see, maybe I can make this bigger and I can write in there a little bit. Oh, I see what happened. The PDF kind of messed up. Sorry about that, guys. It's going to be a little bit cramped for part B. So for part A, it says, normal distribution. So what's the good part? The good part is normal distribution. Once they tell us that, we're good. We also are liking the fact that they gave us the mean of 504 and the standard deviation of 111. These are all good things they need to tell us in order to use our normal distribution. So it says, how high must a student score in order to place in the top 5%? Okay, so I'm going to have to do a little bit of scratch work over here. Let's draw a little bar. So this will be example 2. Okay, so example 2, part A, says how high must a student score in order to place in the top 5%? Well, I'm just going to try to jump right into it. I'm going to go inverse norm. Oh man, I kind of 5%, the top 5%, that's not exactly what I was hoping for because the calculator doesn't go that way. So I'm going to draw my little picture, and the top 5% is going to be like right here, right? It's going to be right here at this point. Oops. So this will be 0.05. That's the top 5%. Now remember, when you use inverse norm, the calculator will not tell you the top 5%. It'll tell you the bottom 5%, but you could outsmart it and use the opposite sign. So if they give you a negative, you just use the positive. Or what I like to do better is I like to just subtract my top 5% from 1, and I'll get 0.95. And then what's my standard deviation? I'm sorry, my mean is 504, and my standard deviation is 111. Okay, so we're going to get inverse norm (504) mean 111, and we get 686 I'll use 3 decimals, 579. Okay, so this is the score that you would need to reach. So it says scores on the SAT recent years follow an approximately normal distribution with a mean of 504 and a standard deviation of 111. This is the score. A 686.579 would be the score that you would need to place in the top 5%, I'm assuming, of the nation. Now, again, I don't know the scoring on the SAT. They keep changing it around. So maybe, because I remember when I was growing up, you were supposed to score like a 1600. So this must be a new scoring system. But in order to score in the top 5%, you need to get a 686.579 score or above. So anything above that would give you in the top 5%. Okay. Now notice I didn't find the Z-score. I didn't find the Z-score at all. I found the non-standard or the unstandardized version of the answer. So this answers their question. If I had to find the Z-score first so I could use the table, then I would have to unstandardize this and find the Z-score that would match. Or I'd have to basically find a Z-score and then turn it into 686.579. So just make sure you guys understand. You could find the Z-score if you need to, but because of the calculator and because of technology, we can jump right into it right here. This allows us to just jump straight into it. And if you're not sure why I use 0.95 instead of 0.05, you can, when we meet later on today, you can ask me about that. Again, I showed in the previous video how you could use the negative version of your answer. So if we had done 0.05, oh no, that actually would not have worked because it was not in Z-score form. So you probably would have to do it this way. So make sure that you understand how I use the 0.95 or ask me about it when we meet next. Okay. Part B. How low must a student score in order to place in the lowest 10%? Now this is a little bit easier. We don't have to outsmart the calculator, right? Because the lowest 10%, we know that's going to be over here somewhere, right? So what number would that be? And we know that that's 0.1, but the calculator already does it in that order. So we're going to go straight into inverse norm, 0.10, comma 504, comma 111. And we're going to get our answer. So we're going to do second vars, inverse norm, 0.10, and everything should still be in there. And I'm going to get 361. We'll use 3 decimals again, 748. Okay, so we get 361.748. So that's the score that you would need to be in the bottom 10%, okay, of the population. All right, is everybody okay with that? Let's see here. Hopefully I have room to do this. How much room will I need? Okay, so for this one, because we're running out a little bit of room, I'm going to try to write it in this space provided right here. Okay. So that probably means I'm not going to be able to draw too much. I'm going to jump straight into the I'm I'm going to jump straight into the normal CDF or inverse norm. It says, recall, according to National Health and Nutrition Examination Survey, the weights of adult men are normally distributed with a mean of 172 and a standard deviation of 29. So again, we're happy they gave us normally distributed, they gave us the mean, and they gave us the standard deviation. These are all extremely important when you're working with normal distribution. It says, above what weight is the heaviest 0.5% of men? Okay, 0.5%. Okay, so what we're going to do is we're going to do 1 minus point. So 0.5%. So that's not even 1%. So that's 0.005. So 1 minus 0.005. Because 1% would be 0.001, right? Or I'm sorry, 0.01. So if we took 0.01 and we divided it by 2, we would get 0.005. Okay, so that means that we're dealing with a half of 1%. So that's where I got this from, by the way, guys. This told me this over here. Okay, and we're doing this so we can find the bottom half of the graph. Okay, so we're going to do 1 minus second function answer, and we get 0.995. So I'm going to do inverse norm 0.995 comma 172 comma 29. And let's see what that gives us. Second verse 0.995 172 29. So we get 246.7. 246 point, let's do 3 decimals. So this would be 700 because it's 699.0498. So I'm going to round to 3 decimals for this. So it says that you would get 246.7 about. So here's the thing. Why did I use 0.995? That actually found the bottom half. But 246 is the same number that finds the bottom half, or it finds the top half of the 5.5%. So I basically kind of just outsmarted the calculator by using 0.995. Now remember, if you use 0.05 or 0.005, the calculator will be giving you the wrong answer. It will be telling you the bottom 0.005%. So what I did is I subtracted the percentages ahead of time up here. So this is me subtracting the percentages ahead of time so I can find the top half instead of the bottom. So I can find the bottom percent and use the calculator to my advantage. Let's do the next one. It says, what weight represents the cutoff for the lightest? Okay. Well, the lightest would be the bottom 12%, not the top 12%. They would be the heaviest. So we're going to do, oops, sorry about that. So we're going to do inverse norm, oops. And then we're going to do 0.12, comma 172, comma 29. Let's see what we get. So second function, inverse norm, 0.12 for 12%. Everything else should be the same. And we get 137.925. Okay, so there's our filled in answer sheet. Sorry about that, you guys. I was running out of room, so I was going to have to fit it in there somewhere. And again, we're using inverse norm a lot because they're giving us the probabilities, and we have to find the unstandardized value or non-standardized value that would create those probabilities, those percentages on our normal curve. Okay, you guys, I don't spend a lot of time on this normally. But basically, how do I say this? We're going to get into the central limit theorem in the next section. So I have like a small little bit animation I'm going to show you guys. But basically, what this is trying to talk to you about in the central limit theorem, it's trying to say, let's suppose we had some kind of distribution. Okay. Oops, that's pretty ugly. let's suppose we had some kind of distribution. And let's say that this was a 1, this was, oops, this was a 5, this was a 6, and this was like a 9 or something. I don't know. So, and basically, we don't know how many of each or anything like that. But as you guys can see, this is not normal. This is not a normal distribution, not in any way, shape, or form, okay? And let's just say we had this distribution, and I wanted to draw a sample of 4. So I'm going to call my first sample, sample 1, and I'm going to draw a sample of 4. And on my first, so basically, I'm going to reach into this bag that has a lot more 1s and 9s than it has 5s and 6s. So if I reached into this bag with all these tiles, and there was a whole bunch of tiles of 1, a whole bunch of tiles of 9, and some tiles of 5, and some tiles of 6, if I were to reach into this bag and pull something out, what would you expect to get on the first draw? Well, maybe I'd get a 9, okay? Then what would you expect to get on the next draw? And I'm going to do draw 4. I'm going to draw 4 things. I'm going to draw 4 samples, okay? On the next one, maybe I get a 9 again. And then on the next one, maybe I get a 1. And on the next one, maybe I get a 5. And this is all just me making it up, okay? I'm going to take another sample, and I'm going to draw 4 more. And maybe this time I get a 1, this time I get a 5, this time I get a 6, and this time I get a 1 again, okay? And then I'm going to take another sample of 4, and this time I get a 9, this time I get a 1, this time I get a 1, this time I get a 9. That could happen because there's more 9s and 1s than anything else. And then I'm going to do S4, and this time I get a 1, a 1, a 1, and a 9. That could happen, you know, and I'm just going through the motions here. Now, what if I wanted to find the means of each one of these samples? We could do S5. Let's say we get weird 5, 5, which is very unlikely, but it could happen, and then 9. Let's say that happens, okay? So now what I'm going to do is I'm going to find the means of each of these. So I'm going to take 9, sorry about that. I'm going to take 9 plus 9 plus 1 plus 5. I'm going to divide it by 4, and I'm going to get 6. So my mean is 6, okay, for this sample. Now let's find 1 plus 5 plus 6 plus 1. 13 divided by 4. We get 3.25. So my mean is 3.25. Now let's do 9 plus 1. So that'd be what, 20 divided by 4, which is 5. So we get 5 for this guy. And then we get, what is that, 13? No, that's 12 divided by 4, which is 3. And then what is that, 20? That's 5 again. Okay, so these are all the means of each one of these samples. So this is the idea behind the central limit theorem, okay, in 6.5. The central limit theorem is saying that even though this distribution up here, this distribution here is obviously not normal, okay? The central limit theorem is saying that this distribution is not normal, okay? However, if you took a sample of that distribution and found the means of each of those means will be normal, okay? So if I took those and I plotted these on a distribution, if I made a distribution curve for this, the mean of the, the distribution of these would be approximately normal, okay? And then eventually would be normal, okay? So that's the idea behind the central limit theorem. So what I'm going to do is I'm going to show you guys a little animation, okay? Now, I found this watching, I believe it was a Khan Academy video. The Khan Academy guy was explaining it with this, the central limit theorem, and this actually helps. So you guys, if you want to see the full video that he was doing, you can go ahead and watch it. But as you see above right there, you guys see that that's normal distribution, right? That's a nice clean curve. So what I'm going to do is I'm going to mess with it. Okay. Now you guys see that there's no way that that is normal distribution still, right? I'll mess it up even worse. Okay. That is not normal distribution. Okay. So what they're going to do is I'm going to draw a sample of 1. Okay. So it draws 5. It's so if you guys notice right here, it drew 5 in this second table with the 5 little things. It took a sample of 5, just the same as I was doing a sample of 4, they're doing a sample of 5, okay? And from their sample of 5, what they're doing is they're finding the mean. So you see the little blue box down at the bottom? In that third graph, that's the mean of the sample they just drew. So I'm going to do another one. They're going to draw 5 more, and they're going to find the mean of that sample. They're going to do it again. They're going to take 5 more tiles, and they're going to find the mean of that sample. And they're plotting the means of all these samples. I'll do it a few more times just so you guys can get the hang of it. I'm just animating this over and over again. And the third graph is the important one. The third graph is the one you want to watch. Now, here's the confusion. Some people get really confused. They're not saying that the original population is normal, okay? And when you draw samples from that, the samples should match the original population. So I should get a lot more stuff when I animate. I should get a lot more stuff on the sides because there's a lot more data on the sides. So on the far right and the far left, I should get a lot of samples from there. I should not expect to get normal. But in the bottom, the mean, the one in blue, that's the one that we are trying to take a look at. So now let me animate 10,000 of these. So it's going to do 10,000 of these draws. Look what it created. So it just did 10,000 samples. You know, it drew a sample of 5. It drew a sample of 5. It did it 10,000 times. And then it plotted the means in the blue. Now let me do 100,000. Look at how close that mean is. The means of the mean is normal distribution. So what the central limit theorem is talking about is it's saying that if you take enough samples, the mean of those samples will eventually become normally distributed, okay? So I want you guys to look at this picture and look at the top graph, obviously not normal distribution, and look at the bottom graph, and that is normal distribution. And then you see the values that it has on the side in blue and purple and red. So look at the means. The top mean is 15.63. The bottom mean on our blue graph is 15.65. They're almost identical. So what you notice, a big part of normal distribution is the mean and the standard deviation. Well, we found a way to work with these means and have the same mean as the original graph. And then if you look at the standard deviation, it's 8.46 and 3.79. Well, those aren't even close to the same. So what I'm going to do is I'm going to show you that if you take 8.46 and you divide it by the square root of 5, because remember, they were drawing a sample of 5. So if you take the standard deviation of the top original curve, the top original distribution, you take whatever that standard deviation was, and you divide it by the square root of your sample size, and we were taking a sample of 5. If you divide it by that, what they're saying is the standard deviations will match. Well, if I take 8.46, the above standard deviation, and I divide it by the square root of 5, which is the sample, guess what I get? I get 3.783, which is basically this standard deviation of 3.79. So that's where they're getting it from. So they're saying that if you take enough samples, the means will match, but the standard deviations will still be off. The standard deviations will still be off. How much will they be off by? They will be off by the square root of n, okay, whatever the sample size was, okay? So that's what the central limit theorem is saying. And again, it'll always work this way. So if I clear everything, look, I can mess this graph up even more. I can make it super skewed on one side and then really low on the other, okay? And then I can animate and draw samples. So I'm doing it again just to show you guys. Now I'm going to do it 100,000 times. And there we go. Now look at the means again. The top mean is 11.29. The bottom mean is 11.28, basically the same, okay? And then the top standard deviation is 6.85. So I'm going to take 6.85 and I'm going to divide it by the square root, square root of 5. And I get 3.06, and this one is 3.0634, and the one here is 3.07. So they're really close to the same. So that's what the central limit theorem is trying to tell you. It's trying to tell you that even if the distribution originally was not normal, if you took the mean of the means, they would match, okay? So let's go back to the notes. So this, the standard deviation of the distribution, so right here, that's what they're trying to tell you right here. You take, okay, you take the standard deviation and you divide it by the square root of n, okay? So sampling distribution of the mean and the central limit theorem, okay? So it says the distribution of the mean is the distribution of the sample means with all samples having the same size and taken from the same population. So that's what I just did over here, by the way, this little information here. And that's what we were doing in the other problem. So what the central limit theorem says so what we're going to do is we're saying before, when we were working with an individual observation X from a normally distributed population, we would just say, you know, it's X is the, you know, we can work with the normal distribution with the mean and the standard deviation, and then Z is equal to X minus mu divided by standard deviation. What they're saying now is that the central limit theorem says, even if that's not the case, if the original population has a normal distribution, then the sample means have a normal distribution. Okay, well, that's kind of easy. But they said if n is greater than 30, then the sample means have a distribution that can be approximately normal distribution, even if the population from which it was drawn is non-normal. So that's what we just did in the previous problem. So it says if the population is normal, then the mean would stay mu. However, the standard deviation would be the standard deviation divided by the square root of n, okay? So I'm just kind of going over the notes right here and here, okay? So we're gonna work with these formulas. And now we look right here and we see, it says when working with the mean for some sample group, be aware that you are now looking at the mean of the sample, okay? So they're gonna draw, instead of drawing one person, we're gonna start drawing like 17 people from a population or 35 people from a population. And we wanna know what's the chance that the mean of that sample is whatever probability. So let's take a look at one. It's kind of a lot of talking. Let's take a minute to try one, okay? So it says the scores of 12th grade students on the National Assessment of Education. Let me get my notes to the right page. So it says the scores of 12th grade students on National Assessment of Educational Progress for the year 2000 math test have a distribution that is normal with a mean of 300 points and a standard deviation of 35 points. Choose one 12th grader at random. What is the probability that his or her score is higher than 350? Now, first things first, they did give us something. They told us that the distribution is normal. They told us the mean, and they told us the standard deviation. So we're good. We have everything we need just like normal. So they want to know what is the probability that his or her score is higher than 350. So we're finding the probability that X is going to be higher than 350. Okay. Well, we know that that's going to be, let's see here, normal CDF. We're going to go from 350 to how far? How high? Well, remember, just pick a random large number, 99999, comma, standard deviation, 300 for the mean, standard deviation of 35. Let's see what we get from that. Is that right? Mean of 300. So I get approximately 0.076. Let's do 4 decimals, 6. Okay. So that means I get this probability of that occurring. Okay. Now, what if somebody asked you to then find the z-score for this or something like that? You could always just convert 350 into a z-score and then go from there, but you would get the same number. Okay, so you could do that. Maybe I should do that for you guys in the next one, or let me, oh, there's not a lot of room. So it says find the probability that the sample mean for a sample of 4 12th graders is higher than 350. So now I got to do a little bit of scratch work over here, or not really scratch work, but just kind of be careful. So now we are going to say, Let's you know what? Let's practice converting the z-score. Okay, so I'm going to make my z-score. Z is equal to x bar. So what are they saying they want x bar to be? Now remember, x bar means the mean. So it says find the probability that the sample mean for a sample of 4 12th graders is higher than 350. So x bar means the mean of these 4 12th graders is 350, minus the mean, which is 300, divided by the standard deviation, which is 35. But here's the catch. It's 35 divided by the square root of 4, because there's 4 12th graders, right? So let's see what we get this time. So 350 minus 300 would be 50, divided by, divided by 35 divided by 2. 2.857. So I get 2.857 for my z-score. So again, remember what we're doing here. We're doing our normal curve, right? And that means here's 0, and then 2.85 is way over here. 2.857, okay? Now keep in mind, we already kind of know, and they want to know the shading. What way is the shading? The shading is this way, because they want to know, find the probability that the sample mean for the sample of 4 12th graders is higher than 350, okay? So again, if the mean is 300 and they're at 350, you already know they're above the mean and they're more than a standard deviation away. So we got a z-score of 2.857, okay? So that means I can now do normal, oops, let me use the other marker. I can now do normal CDF with 2.857, comma 99999, comma 0, comma 1. Why am I able to convert everything to 0 and 1 now? Because I found the z-score. So now I'm working in standard normal again. Okay, so we're going to do second bar's normal CDF of 2.857, 0, comma 1. And I get approximately, let me go over here a little bit, 0.0021. So very small, that's 0.2 of 1%, okay? So that's 0.2%, all right? Now, if you're saying, well, why did we have to do the z-score? We didn't. I just wanted to show you what we could have done instead is this is option B. We could have done normal CDF. We could have said 350 to 9999999. And we could have done the normal, the mean of the original problem was 300. And what is the standard deviation is 35, but you can't do 35 because you're doing the mean of these 4 12th graders. So you divide it by the square root of 4. And let's see what we get on our calculator. So let's do normal CDF. Now think about this in your mind. What should we get? That's the question. What should we get? Well, we should get the same exact thing that we've been doing. Or, you know, really darn close within a rounding error. Oops. And I do. I think I get it off by 1/1,000,000th of a place value. So I get 0.002137. So same answer. So as you guys notice, these are both the same answer. Okay. So you could have done it either way. One way, you find the z-score first, you convert it to a z-score. Remember, I'm doing the exact down here. I'm doing the exact same graph. So this is supposed to be like that. And I'm still doing the same exact thing. I'm over here at 350, but this time I'm doing the sample mean, so I'm over here. I'm doing the same graph as above, but instead of the mean being 0, I'm using a mean of 300, okay? So you can answer that question either way you like, whatever way works best for you. So let's do the rent example. Okay, so it says the price of renting an apartment in a city of San Diego follows a skewed distribution with a mean of 715 and a standard deviation of $135. Suppose the rental prices for a random sample of 75 San Diego apartments is collected. Describe the sampling distribution of the sample mean rental price for 75 apartments. Okay. So when they say describe the sampling distribution, they just mean do this. You'll see this sometimes in your homework. They just mean X bar is approximately normal with a mean of $715 and 135 divided by the square root of 75. Okay, so let me just scroll up here real quick. Okay. All right, sorry about that. I just wanted to check something real quick. So part B says, what is the probability that the average rental price in the sample is less than 685? So think about this again. We're doing our little drawing. And they want to know that remember, we're drawing 75 apartments. We're drawing 75. So even though this distribution is skewed, we're allowed to treat it as approximately normal as long as we calculate using 135 divided by the square root of 75. That's what the central limit theorem is promising us, okay? Because the sample size is 75. Even though the distribution is not normal, we can still work with it like it is, okay? So mean rental price for 75 apartments is less than 685. So I don't know where that's at, but let's say 685 right there, and we want less than. Now, again, this is for the mean of the sample. So we're going to just do normal CDF. Oops. And then we're going to use, so we could convert it to a z-score, but why do it if we have the technology? Let's just jump right into it. We're going to do negative 99999, 685, comma, 715, comma, 135 divided by square root of 75. Let's see what we get on our calculator. So I get about 0.0271. Yeah, if I use 4 decimal places. And in general, for probability, we're going to use 4 decimal places. So we get 0.0271. And again, the 715 came from there. And the 135 over square root of 75 came from there. So that's how we can adjust for the fact that it's not normally distributed, but we had a sample size above 30. Okay, that's what the central limit theorem promises us. Okay, how much do we got left? Okay, we're almost done, guys. We just got a little bit left, and then I'll post this video for you. So it says, in engineering, weights of people are considered so that the airplanes and the elevator aren't overloaded. Chairs won't break and other embarrassing things won't occur. Men's weights are normally distributed with a mean of 175 pounds and a standard deviation of 25. An elevator in the Cesar Chavez building has a weight limit of 18 people or a total of 3,500 pounds. What is the probability that a randomly selected man weighs more than 190 pounds? Okay, so let's see here. We're going to do randomly selected man, probability that X is more than 190. We know that's just normal CDF. We don't even have to do anything special. 190, because it's just one individual. What do they say? 175 mean and a standard deviation of 25. Now again, why am I not dividing by the square root of n? Well, technically, I guess you could say I am. What's the square root of one man? Well, that's just the square root of 1 is 1. So it's like you never even noticed. So let's see what we get when we do that. So normal CDF, 190. And again, I'm going to the right because they said more than 190. I kind of glossed over that, but make sure you understand that why I'm not going negative 99999 to 190. That would be less than 190. I'm going more than 190. So I get approximately 0.2743 if you round off. That would be our answer for that. And again, you guys, while you're doing these problems, feel free to pause the video to see if you can answer it before I start going into it, and then kind of compare our work and see if it's making sense to you. So maybe now try the next one without my help. The next one's a little bit harder. It says if 18 men are randomly selected, I should say part C is harder. If 18 men are randomly selected to be in an elevator, what is the sampling distribution of the sample mean? Well, they're just asking for the X bar again, and that's basically normally distributed with 175, let's say approximately normal, and 25 divided by the square root of 18. So this is how we can adjust our standard deviation. It says, what is the probability that their average weight will exceed the weight limit? Well, how do you find average weight of 18 men? And what is the weight limit? So what we're going to do is we're going to exceed the weight limit. So that means we're going to do normal CDF. Okay, now you got to think about it. What is the weight limit? Well, they said up here in the problem that the weight limit is 3,500 pounds. Okay. And we're taking a sample of 18 men, okay? So what we're gonna do is we're gonna do 3,500 pounds divided by 18, okay? So 3,500 divided by 18. So that would be 194.44, but just so I don't have a lot of error, I'm just gonna leave it as 3,500 over 18. I'm allowed to plug that in my calculator. And then it's going to exceed the weight limit. So is that below this number or above this number? Well, we're going to go above. So we're going to go 99999. We're trying to find the area above. And then we're still going to use 175. And we're going to use 25 divided by the square root of 18. Now, remember, most people have a hard time with this problem because they're not sure how to account for the fact that they say the average weight will exceed the weight limit. So that means if you have 18 people on this elevator, all 18 of them on average exceed the weight limit allowed per person. So we have to find out what the average weight limit that would be allowed is. Well, the average weight limit that would be allowed is 194 pounds per person. So they're saying, what's the probability that all 18 of these people on average exceed that 194? Okay, so 194.44 is 3,500 divided by 18. So we're going to find that. And again, this is a little bit harder problem. So let's do second vars, normal CDF. I'm going to leave it as 3,500 divided by 18, just so I get a more accurate number. 175 is still correct, but now I got to do 25 divided by the square root of 18. Okay, and I get, oops, something went wrong there. This is second vars. Sorry about that. Something went wrong on my calculator. Let's see here if that's right. I got a very, very small number. Well, I guess I should. Yeah, I got 4.83, oops, 8377 times 10 to the negative 4. So in your calculator, you guys probably got 4.837725 blah, 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 or 26299 times 10 to the negative 4. It'll say e to the negative 4, but that means times 10 to the negative 4. So this is the correct answer. Okay, but if that doesn't make sense to you, let's write it for what it is. What does 10 to the negative 4 do to a number? Well, you take 4.8377 and let's move the decimal place 1, 2, 3, 4 places. And that's our new decimal place, and we put zeros in its spot. So that means that this is actually equivalent to 0.00048377. So this is the written out decimal. This is scientific notation. Okay. So this is scientific notation. This is standard decimal form. I would take either, but it's important that if you leave it in scientific notation, 4.8377, you understand what that means when you multiply it times 10 to the negative 4. You're basically saying it's a very small amount. And should it be a small amount? Yes, this isn't even a tenth of 1%. This is 4/100ths of 1%. But now think about this. Don't you want that to be a very small percentage? Because if it goes over that, the elevator has a capacity. Something could break or something bad could happen or the elevator gets stuck. So they're saying, what's the chances of this actually happening, of all the people getting in the elevator that are all over the average weight limit? They're saying the chance of that, their average weight is over the weight limit. They're saying the chance of that happening is 4/100ths of 1%. So very, very unlikely, which is what I want. What I want from my elevator, I want it to be able to handle that. Okay, so let's see, we're running out of time. Let's see, you guys. So I did the ramp one. Okay. Now that is actually the last problem I have in my notes. Oh no, I have this body temperature one as well. Okay. I just wanted to make sure. So it says, assume that body temperature populations, assume the populations, their human body temperature has a mean of 98.6. Also assume the population has a standard deviation of 0.62 degrees Fahrenheit. A sample of 106 randomly people is selected. So why is the 106 important to us? Think about that. Why is the 106 important? Well, did they say anywhere in here that the population has a normal distribution? They didn't, right? So the 106 lets us still use normal distribution because the 106 is larger than 30. Remember, if we go way up here to the central limit theorem, the central limit theorem says if n is greater than 30, then you can still treat it as approximately normal, okay? So we're gonna go here and we know that we have 106 people, so we're gonna be okay. So we're gonna say that x bar is approximately normal, oops. And we know that we have a mean of 98.6 and a standard deviation of 62 divided by the square root of 106. And later on, we're gonna do a study, or not a study, but we're gonna follow a survey that talks about, is the mean of the population really 98.6? And we'll gather data from a study and it'll tell us that maybe it's not. Maybe that's just kind of something that people have gone with, but it's actually incorrect. So it says, what is the probability that the average temperature for a sample of 106 people to be 98.2? So that means you take 106 people and you find their average. What's the chance that that average is 98.2 or lower? Okay, so that means below, right? So we're gonna do normal, normal CDF. And we're going to go negative, because we're going below, we're going to go negative 99999, comma, 98.2, what they asked. The mean is 98.6, and we have a standard deviation of 62 divided by the square root of 106, because we have a sample size of 106. So we should get, let's see, let's plug it in our calculator. Second verse. Now, would you expect this to be a small number or a large number? I'm thinking it's going to be a very small number. Because if the mean is 98.6, what's the chance that of the 106 people, their average will be below 98.6 on average? It's very unlikely, but let's just see if I'm right. Sometimes in math, if you question what your answer will be, it's kind of like you're verifying or validating your thoughts. It can really help you start grasping things a little bit better if you're making guesses. Oops, I think I did something wrong. Oh yeah, okay, I entered it in wrong in my calculator while I was talking to you guys. So we're gonna go negative 99999, 98.2. My calculator is not working properly right now. Okay, so second vars, normal CDF. Did I write this correctly? 62. Oh, it's 0.62. I was going to say 0.62. Sorry about that, guys. Go back and fix that. I was like, so I was getting about 50% chance. And I know because of my guess, I know that that can't be right. I know it should be a very small number because the likelihood of this happening. So in this case, my guess saved me from making a mistake right now. 0.62 divided by second vars. Oops, not second vars. It's 0.62, not 62. Yeah, I kept getting that. Did I do it again? Well, you guys, I can't get it to work on my calculator right now. I'm going to have to just tell you the answer. The answer is 1.529 times 10 to the negative 11, which again, you should know is a very, very small number. It says, based on the probability above, is it rare for the average body temperature for a group of 106 subjects to be 98.2 or below? And you would say, yes, that's less than 5%. So we go up here to the rare event rule. If under a given assumption, the probability of a particular observed event is exceptionally small, we conclude that the assumption is probably not correct. Usually if probability is below 5%, we say the event is rare. So yes, 1.529 times 10 to the negative 11 is below 5% chance, okay? So we would say, yes, this is rare. I'm gonna have to mess with my calculator, guys. I don't know what I did to it. Something's going on in there. But yeah, it should be a very, very small percentage chance that on average, you get 106 people to have this probability or to have a mean of 98.2. Okay. All right, you guys, that's going to do it for today. See you in our next lecture and hope this helps. Okay.